Thanks very much, Julian. So next slide. Today we're going to be talking about shape-dependent light scattering. So a little bit different from the previous talks, but stick with me and I'll be as explicative as possible, and hopefully you'll grab some of the takeaway messages. Okay, I'm talking mostly about the results from this 2014 paper and some follow-on work that we've been able to do. This is about spectral bluing and how it's caused by small particles and submicron sized particles. All right, so next slide. Three takeaways of the talk are, the first one is that spectral bluing occurs not just for particles in our atmosphere like fine hazes and aerosols, but also for particles, small particles, submicron sized particles embedded in targets, embedded in solid targets like ices and so on. And the new finding that I'm going to be talking about today is that when you have aspherical particles, so not perfect spheres, which the paper talked about, but looking at aspherical particles, that oblate grains are stronger in their bluing capabilities, so they cause more bluing than prolate particles, and we'll go into why that might be and some of the results. And then the final bit is I just want to talk about the implications for exploration of Bennu and what we might expect to learn from OSIRIS-REx. Next slide. First one, next slide, is spectral bluing can take place in all sorts of situations. And here we see an example of moonshine of the Earth's spectrum here. And you can see just here is what I'm talking about, is this spectral bluing effect where the Earth looks bluer in the UV area because of the presence of our atmosphere and aerosols in the atmosphere, submicron sized particles. But this is not just an effect that's limited to the atmosphere. Next slide. In fact, Roger Clark was able to show that when he embedded carbon black particles, submicron sized particles, they had a size of about 0.2 microns, into ice targets, that he was able to create a spectral bluing peak here. He also used the word Rayleigh scattering in his paper. I prefer to just use spectral bluing because Rayleigh scattering is intimately associated with the atmosphere. So next slide, please. So in the paper, I'm just going to go over this plot here, which is of interest because it shows you where in the spectrum you might find spectral bluing taking place. So it's, we'll just concentrate on the top left-hand plot, and it has a color graph here. And this shows you basically the derivative of the spectral bluing peak. It shows you where it actually shows up on in terms of the size parameter of the particle. So when we convert that to a certain size particle, and well, you can't see here, but that's 1 micron. I'll just make the equivalence here, 1 micron here. Then you get spectral bluing in the shortwave infrared, which is between 2 and 2.5 microns. So this sort of graph, which was produced for Rayleigh scattering, can also be converted to Mie scattering. Go to the next slide. And we get similar sort of results. We get a dark side on the right-hand side, which is the infrared side of the spectrum. And this is the UV side of the spectrum, where all that Rayleigh scattering is happening, or spectral bluing. So you get a gradient across here just due to the particle sizes being so small relative to the wavelength. So this is all well and good, but it's just for spherical particles. So now we want to extend that to aspherical particles. Next slide, please. Oh, and this just shows you an example lookup table. If you have that are produced for the paper, and if you make some reasonable assumptions about the particle characteristics, then you can actually pull out a grain size from looking at where the spectral bluing actually occurs in your spectrum. All right, go to the next slide, please. And this just shows you that we tried this on a range of size distributions in the paper and found for sharply peaked size distributions, you get very similar to single particle scattering. And then as you expanded the size distribution, you actually get down to across this area of the plot where you actually see a peak and then a run down on the other side. So you can see a turnover. And if you're a spectroscopist, you probably have often seen that turnover in the very UV region. So that could be due to size-dependent, grain size-dependent effects. So next slide. Okay, so oblate grains show stronger scattering or stronger bluing than prolate grains. Next slide. All right, and if you could just start the video there. So what I have here is prolate and oblate grains shown. You can see the oblates are a little bit fatter on the sides and prolates are more tall like me. So you can make your own inferences from that. But here we have an example EM spectrum or incident light hitting this oblate grain. And we have this in red going up and down. Here is the electric vector here, magnetic vector is out to the side. So this is going on and hitting the oblate grain size directly on. And when you have an oblate grain, so you start off with a sphere and then you push it down into an oblate shape, and you're actually making it smaller in the dimension that the electric spectrum or that the electric vector is sensitive to. So you are, in fact, creating or making a smaller particle when you have an oblate grain that's being illuminated. And so that it shouldn't be much surprising, or very surprising, that in fact you get greater spectral bluing when you get these fatter oblate spectra, the stored particles. Next slide. And that's indeed what you see. So we start off with the prolate grains, and what I'm showing here is again the size parameter running along the bottom here, and the scattering efficiency, which is just a measure for how much scattering is taking place at that part of the spectrum. And this is the spectral bluing peak of the region. So you actually see that for a nearly spheroid particle here with a over B, which is just a measure of how prolate it is, and I've sized and I've shaped these grains to show you exactly what their aspect ratio is. These are actually two to shape anyway, to scale. So the green grain, which matches this one here, has the strongest spectral bluing because the peak goes up the fastest. The derivative is the fastest. Whereas the red one, which is prolate, a little bit like me, has the least bluing because it's actually effectively creating a bigger particle. Does everyone follow that? All right, you can ask me in the question time anyway. Next slide. And the reverse happens for the oblate grains. So as you're getting a more oblate particle, it actually makes more spectral bluing, and the derivative is greater for this for the scattering efficiency in this part of the spectrum. So the oblate grain here is the winner in terms of most efficient spectral bluing particle. All right, so next slide. So the final takeaway is that we can actually investigate Bennu, and we actually have good reason to think that spectral bluing is happening on Bennu, and it's an extremely fascinating case. So let's go on to the next slide. This is just an example of some of the spectra that just to show you a rogues gallery of targets that show spectral bluing. We have several in the Saturn system, imaged by Cassini. This is Comet Holmes here, showing some spectral bluing here. Even on Mars, we see some examples of spectral bluing in the polar regions as well. Next slide. And we have some meteorites. We have meteorite spectra here in the dots of this meteorite spectra here that Beth Clark published in her 2011 Icarus paper, where she was trying to match up the spectral bluing effect to crushed particles from her laboratory. Next slide. So this is the really interesting example from Bennu. These are all observations of Bennu from 0.5 to 2.5 microns. And in particular, the red and the blue, I want you to draw your attention to the red and the purple plots, where they do actually see spectral bluing happening in the 0.5 to 0.9 micron region. Now, these are observations that were taken in 2011, 2013, or at least reported in those years. Then there were follow-up observations of Bennu that didn't actually cover that region, but had a pronounced red slope out here in the 1 to 2.5 micron region. And Ralph Benzel actually put this together and suggested that Bennu, because it had actually shown a different face to the Earth and to our observers here, that there was variations on the surface of Bennu that were showing up and creating this this spectral bluing feature, which was then lost in subsequent observations. Next slide. What are we to make of this? How can we make anything of it? So this is a gravity shape model of Bennu, and it's thought to have an equatorial ridge, or it does have an equatorial ridge, thought to be caused by the Yorp effect, it's possible that there is some shape and grain size sorting that's happening on Bennu because of the variable gravity on the surface. We have the gravity here around the centroid of the body is the lowest and is the highest up here. So that's going to have some sort of effect on grain size, grain size, and potentially also on orientation that we'll be able to get at spatially when we have a spacecraft in orbit taking observations. Next slide, please. That spacecraft, of course, is OSIRIS-REx, and the instrument that's going to do it is OVIRS. Very conveniently, they have spectral coverage from 0.4 to 4.3 microns, so they should be able to capture that spectral bluing, which we haven't been able to see recently from Earth-borne observations. And they will be creating 20 meter resolution maps of the surface. So this is all fantastic. And I just want to sum up with the last slide, which is a little bit more of implications for dynamics and cohesiveness of asteroids. So in 2014, Ben Rosides was the author of this paper in Nature, where he concluded that cohesive grain forces were actually required in order to keep 1950 DA together because it has such a fast spin rate. Its spin rate is just faster than the 2.2 hours that would be required to keep together a cohesionless asteroid. So they invoked a particle sticking model and said that if they had similar cohesion to particles on the moon, then they could keep the asteroid together with those cohesive forces. Their model, in fact, induced them to suggest that everything bigger than 6 centimeters would be excised from the surface of this asteroid because of these cohesion forces not being able to hold anything greater than that. So that's a really sort of interesting, this is a different body, of course, and Bennu has a much longer period, but it's these sorts of cohesion parameters that we could get out of back modeling our models of the regolith that we will be able to map using OVIRS and the surface of Bennu in the coming years. Thanks very much.
Thank you. We have time for one question.
Thanks. This is interesting stuff. In order to get the bluing of the spectrum, does do the submicron particles have to dominate in some
Yes.
sense?
Yes.
So there has to be a very large mass fraction of them?
Yeah, absolutely. Yes, they have to be on top of the surface. Yeah, they can't be buried at all. This is a very much a surface effect, so you need to have them on top of the surface. Of course, that's also in some ways a strength of the observation, because you can say, well, this is definitely on the surface. But yeah, they do have to be the dominant size grain. And as I showed you, if you have more particles interacting that have a large spread and size distribution,